Hello everybody. Today we are going to discuss this part, that is the transformation of random variables. We discussed about the different kind of discrete and continuous distributions in our previous lectures. And today we are going to study the transformation of random variables. What is this? Suppose we have a random variable x and small x be a real number, and we corresponding to this real number small x, let us consider a function or a transformation g, that y is equal to g of x, a function of x or a transformation from x to the variable y. Then in terms of random variable, the corresponding transformation can be written in the way that y is equal to g of x. All right. If small y is equal to g of small x, then capital Y is equal to g of capital X. And now, if the distribution of x is known to us, if the probability distribution of the random variable x is a known distribution, then the problem over here is to find out the distribution of y or g of x. How can we find the distribution of y or distribution of g of x from the distribution of capital X? All right. So this is called the study of the transformed random variable, or you can consider that from x random variable to y random variable, we are considering this kind of transformation. Hmm. And from the distribution of x, we are going to find out the distribution of y. Now it can be proved that if this function g is a continuous function, then we can uniquely determine the distribution of y from the distribution of x. But the proof of that result is very difficult, and we are not going to discuss this proof. We are actually going to discuss a particular case of that result. Over here, we are considering the particular case that g should be monotone increasing or monotone decreasing function. G should be a strictly monotone increasing or strictly monotone decreasing function, and its derivative should exist, so that the derivative of g with respect to x would be positive when g is strictly monotone increasing function, and the derivative of g with respect to x, or you can consider that we are considering this derivative dy dx. Derivative of g with respect to x, then that can also be written in this way, dy dx. If this derivative is strictly positive, then g is strictly monotone increasing, and if this derivative is strictly negative, then g is strictly monotone decreasing. And for these two cases, we are going to find out the technique by which we compute the distribution of the probability distribution of the random variable y. And it is expected that if the distribution of the random variable x is a discrete distribution, then the corresponding distribution of y is also expected to be a discrete distribution. And if x has a continuous distribution, then y should have a continuous distribution over here. So these are some known important results or important facts that we should observe, and we should be very careful about the notation of this transformation g. You see, generally we make this kind of mistake, that y is equal to, we write y is equal to g of x, and sometimes we write y is equal to capital G of x, because everything is written in terms of random variables. Therefore, we write y. Sometimes we make this mistake that we write y is equal to g of x. But you see, just in place of small x and small y, we are putting capital X and capital Y over here. So this function g should not be changed to the function capital G. The function g may be a sine function, capital G may be a small, maybe in another kind of maybe cos function or tan function or a polynomial function. So we should not change the rule or the function. Got it? Therefore, this is a wrong notation. This is a wrong notation. Y is equal to small g of x should be the correct notation. I have written all this over here as a remark. Hmm? So be very careful about this kind of misleading notation. This kind of notation, y is equal to g of x and y is equal to small g of x. These are totally two different transformations. So be very careful about this kind of transformation when you are going to write all this in exam. Hmm? Now let's try to find out the distribution of y. We are discussing this case for two different distributions. One is for continuous distribution, another is for discrete distribution. First of all, let us prove the result for continuous distribution. The transformation formula for continuous random variables. All right. So suppose that x and y, x is a continuous random variable, then y should also be a continuous random variable. Now, how to compute the distribution of y? We know the distribution of x. That means we know the spectrum of x and the density function of x. All right. Then our target is to find out the spectrum of the random variable y and the corresponding density function of the random variable y. So if spectrum is given, spectrum should be is generally given by this kind of by this kind of inequalities like a less than x less than capital B, this kind of inequality or something like that, minus infinity less than x less than maybe some constant or maybe plus infinity, etc. So we generally get this type of inequalities, and over here we are considering a strictly monotone function. What is the property of strictly monotone function? The property of the strictly monotone function is that let us show a strictly monotone function over here. You see this kind of function, these are the strictly monotone functions, and in this kind of strictly monotone function, you see, suppose this the domain of definition of this kind of function is from a to b, depends upon the spectrum of x. Maybe from a to b we get this kind of domain of definition, and correspondingly the corresponding domain of definition may be from c to d depending upon the nature of the transformation, that is the function g. Okay. Now over here, in case of monotone function, it's a very important property, that is corresponding to each value of x. Corresponding to each value of x over here, we get one and only one value of y. That is the main property of strictly monotone function. Whether it is monotone increasing or decreasing, it doesn't matter. Okay, corresponding to each value of x over here, suppose this is the value of x, then we would get only one and only one value of y, not more than one value of y, and corresponding to each value of y we would get exactly one x. That means we can say that the function g inverse exists. This original function g is would be a one-to-one function, and and therefore the inverse function g inverse would exist. And it can also be proved that in this kind of cases, as because the function g is continuously differentiable, the derivative this inverse function is also a continuously differentiable function. What is continuously differentiable function? Continuously differentiable function means that the derivative of g, that is g dash of x, this derivative should be a continuous function, and it means that the inverse function should have same kind of property. That means the inverse function should have a continuous derivative. This is called continuously differentiable function. So these are the properties that follows from the fact that this transformation g is a continuously differentiable function and it is strictly monotone function. Got it? the inverse function would also be continuously differentiable, and it would be a strictly monotone function. So these are few properties of continuously differentiable function. And in this kind of cases, we can prove that the density function of y, we are writing the density function of x by the suffix f suffix x, by this suffix x, and f of y that represents the density function of y, because over here we have two random variables, so we need to distinguish them. So that is distinguished by introducing this kind of suffix x or y. All right. So this is the formula by which we can compute the density function of y from the density function of x. And we are going to prove this result. How to prove this result? Over here, you see we are given that the function g is a continuously differentiable function and it is strictly monotone. Strictly monotone means the derivative dy dx, the derivative of g, or dg dx or dy dx, whatever you call, this derivative must be either greater than 0 or strictly less than 0. So that we can say that the inverse function g inverse exists and it is also continuously differentiable. Now we consider this proof in these two different subcases. The first case one, let us consider that dy dx is greater than 0. If dy dx is greater than 0, then y is equal to gx is a strictly increasing function. All right, and if this y is equal to gx is a strictly increasing function, we are going to show that x less than is equal to capital X and y less than is equal to small y. Sorry, x less than is equal to small x, that means random variable capital X less than is equal to small x, and the random variable capital Y less than is equal to small y, both are two equivalent events or same or identical events. That means from first event we can prove the second event, and conversely from the second event we can prove that the first event is also true. Now how to prove this result? Let me show this result from here. You see, consider the case when dy dx is strictly greater than 0. So strictly greater than 0, it means that g should be a strictly increasing function. So if we suppose that x is less than is equal to small x, capital X is less than is equal to small x, then as because g is a strictly monotone increasing function, we can say that g of capital X that should be less than is equal to g of small x. If we have strict inequality over here, then we should also get strict inequality over here as well. Anyway, over here we need this kind of less than is equal to symbol. So we can say that g of capital X should be less than is equal to g of small x. And what is g of capital X? G of capital X is equal to y, and g of small x is equal to small y. So we can say that y is less than is equal to small y. So from this first inequality, that means capital X less than is equal to small x, we have proved this second inequality, y less than is equal to small y. Now, if we conversely suppose that y is less than is equal to small y, then on both sides we take the function, we operate from by the function g inverse. Therefore, we would get as because g because g is a strictly monotone increasing function. I told you that g inverse should also be strictly monotone increasing function. Now, since g inverse is a monotone increasing function, therefore we can conclude that g inverse of capital Y that should also be less than is equal to g inverse of small y. And what is g inverse of capital Y? G inverse of capital Y must be is equal to capital X, and g inverse of small y must be is equal to small x. Thus, what we observe is that y less than is equal to small y implies that capital X less than is equal to small x. So we can say that this x less than is equal to small x and capital Y less than is equal to small y, both of these two are equivalent event because one event implies the other event. And therefore we can say that the probability of these two events, this event can be written in this way, that minus infinity less than capital X less than is equal to small x, and this can also be written in this way, that minus infinity less than y less than is equal to small y. Therefore their probability must be same. Let me show you from this file. So we can say that probability minus infinity less than x less than or is equal to x. This probability should be less than should be same as the probability that minus infinity less than capital Y less than is equal to small y. And what are these two quantities? These are actually the distribution functions of x and y. So this is actually the definition of distribution function. Probability that minus infinity less than capital X less than is equal to small x. That is actually the distribution function of x, and we are representing it as capital F suffix x of x. This suffix represents that this capital F is actually the distribution function of x, and over here the distribution function of y is represented in this way, using this kind of suffix y, showing that this is actually the distribution function of y. So do not mix these two distribution functions. Although we are representing all these two distribution functions by capital F, but in order to distinguish them we are using this kind of suffix x or y over here. And now we differentiate this relation with respect to x. If we differentiate this relation with respect to x, on the left hand side we will get the derivative of this fx, and on the right hand side we will get derivative of the function fy. But by chain rule, y is to be differentiated with respect to x, so that we would have dy dx over here. And this derivative of distribution function gives us the density function. So over here, this is the derivative of the distribution function. It gives us the density function of x, and similarly, the derivative of the distribution function of y would give us the density function of y. So we will have this kind of relation, that fxx is equal to fyy into dy dx, and therefore this fyy, this density function fyy, can be written as fxx divided by dy dx, or this 1 by dy dx can be written as dx dy. And you see, as because this dy dx is greater than 0, therefore this dy dx or dx dy both should be greater than 0, and therefore we can use a modulus symbol over here, showing that this required result is true for the first case. The first case means when the function g is strictly monotone increasing. Okay. And now we are going to prove the same result for the second case. Second case means we should assume that the function g is strictly monotone decreasing function. That means dy dx should be negative quantity, strictly negative quantity. Okay, so we consider this second case over here. You see, in this second case, we have dy dx less than 0. Dy dx less than 0 means dx dy is also less than 0. And of course, as because g is strictly in monotone decreasing, so the corresponding function g inverse, that should also be strictly monotone decreasing function. Okay, and x less than is equal to small x implies g of x greater than is equal to, opposite kind of inequality would appear, greater than is equal to g of small x. Therefore you would have y greater than is equal to small y. Again, y greater than is equal to small y implies that g inverse of y less than is equal to g inverse of small y. Why? Because of the fact that g inverse is a strictly monotone decreasing function. So this greater than is equal to symbol will become less than is equal to symbol. Got it? And what is g inverse of y? G inverse of y would be is equal to x, and g inverse of small y would be is equal to small x, the real number small x. This is the random variable and this is the real number. So we observe over here that x less than is equal to small x is equivalent to the event that y less than is greater than is equal to small y. Over here y should be greater than is equal to small y, as because of the fact that one event implies the second event. Okay. Thus, we observe that these two events are equivalent events or same events. Therefore, their probabilities must be same. Got it? Over here, this x less than is equal to small x can be written in this way: minus infinity less than capital X less than is equal to small x. And this event y greater than is equal to small y, probability of this quantity can be written in terms of the complement of the event. Y greater than is equal to small y. The complement of that event would be is equal to capital Y less than, strictly less than small y. And what would be the lower limit of that capital Y? That would be minus infinity, of course. So minus infinity less than capital Y less than small y is actually the complement of the event that capital Y greater than is equal to small y. Okay, so probability of this event can be written as 1 minus probability of the complement of this event. And I am showing from this file over here. So we have this much, and this first left hand side, this left hand side can be written as this kind of distribution function of x, and this expression can be written as this kind of distribution function of y. You see, I have made a mistake over here, printing mistake, that should be strictly less than y. Although this is correct because in case of continuous distribution, just inclusion of one point does not change the probability. We know that in case of continuous distribution, the probability of a single point is always equal to 0. Therefore, you can also write less than is equal to symbol over here. Mathematically, it is correct. Although this event, including this equality symbol, this event would not be the complement of this event. So, in order to stress on the fact that we are considering this complement, we should delete this inequality. Anyway, so this value of this probability, this expression, value of this expression would actually be equal to the distribution function, because just inclusion of only one point y or deletion of that point y, it doesn't change the probability at all. Okay. So mathematically speaking, this is correct, but this is not the complement of this event. All right. Anyway, so we differentiate this relation with respect to x, and after differentiating, we would get this f dash of this fx, the derivative of this fx, and on the right hand side, we would get the derivative of fy with this negative symbol, and we will have dy dx over here. And therefore, as because we got the derivative, these derivatives are actually the density functions over here. This is the density function of x, and this would be the density function of y, and therefore this density function fyy can be written as fxx divided by dy dx, and this dy dx can be written as dx dy. And in order to suppress this negative symbol, because of the fact that dy dx itself is a negative quantity, this dy dx itself is a negative quantity, so altogether within this negative symbol, the total expression within bracket, this total expression becomes a positive quantity. And that can be written by modulus of dx dy. Got it? So what you observe is that this relation is also true in case of this second result, that means when dy dx is strictly less than 0. Okay, so this is the proof of the result for continuous distribution, and for discrete distribution the proof is much more easy, because you see, suppose in case of discrete distribution, if we have this kind of transformation y is equal to gx, in that case what we observe that if g is a strictly increasing function or decreasing function. What I mean to say is g is a strictly monotone function. Therefore, we can say that if x is equal to this xi, okay, this x is equal to xi, then it would imply by taking that g of x, this g of x would be is equal to g of xi, g of small xi. Okay, xi is the xi, this is the spectrum of x. And what does it mean? It means that g of x means this y is equal to g of small xi, that is actually our yi. Similarly, if y is equal to yi, then by opposite kind of transformation formula, that means by g inverse, we can prove that x is equal to xi. What I am trying to say is that x is equal to xi and y is equal to yi. These two are actually equivalent events. We can prove that x is equal to xi implies y is equal to yi, and conversely we can prove that y is equal to yi implies that x is equal to xi is also true. Got it? So we can say that probability of these two events must be same. Probability of this event and probability of this event, probability y is equal to small y, their probabilities must be same. Got it? So let me remove these symbols over here. We can say that simply probability that x is equal to xi is equal to probability that y is equal to yi, and that's why probability of x is equal to xi gives us the probability mass function of x, and probability that y is equal to yi gives us the probability mass function of y. Therefore, the value of the probability mass functions of x and y must be same for all values of x and y. Got it? And what would be the spectrum? Yi is equal to g of xi for all values of I. This would give us the spectrum of y. So in this way, the proof is shown over here. What I have computed earlier. In this way, we can prove that the probability at the points of the spectrum do not change, only the spectrum changes, and spectrum is given by this kind of transformation formula: yi is equal to g of xi. So that is the transformation for discrete random variables. The first problem says that if x is a normal variate with parameters m and sigma, then this kind of transformation y is equal to x minus m divided by sigma, this kind of formula, this y would follow a standard normal distribution. This is the symbol that y follows a distribution. And what kind of distribution? This distribution given by normal 0 1, that means 0 is the mean and 1 is the standard deviation of the distribution. This kind of distribution is called standard normal distribution. Okay, so we have to prove that we shall need to compute the spectrum of this random variable y and the corresponding probability density function of the random variable y from the probability density function of x, of course. Over here you see x is follows a standard normal, x follows a normal distribution with parameters m and sigma. So this would be the spectrum minus infinity less than x less than small x. And this is the density function of in the random variable x, 1 by root over of twice by sigma e to the power of minus half x minus m by sigma whole square. And whenever you write a density function, do not forget to mention the corresponding range of the parameters. Over here, the first parameter small m varies from minus infinity to plus infinity, and the parameter sigma is a positive parameter. If you do not include these ranges, in that case the definition of the random variable x or the probability distribution is an incomplete definition. Okay, so be very careful about these ranges of the parameters. Without the range of the parameter, the distribution does not have any meaning at all. Okay, now we consider this transformation formula: y is equal to x minus m divided by sigma. and therefore in terms of real variable we should write y is equal to small x minus m divided by sigma. And you see, if we differentiate this expression, if we compute dy dx is equal to 1 by sigma, and as because sigma is positive, therefore this dy dx is strictly greater than 0. That means y is an increasing function, strictly increasing function, or strictly monotone increasing function of x. Okay. And over here you see, if x varies from minus infinity to plus infinity, and as because m is an infinite real number and sigma is a positive quantity, therefore this expression x minus this kind of finite number divided by positive quantity, that should also vary in between minus infinity to plus infinity. Okay, therefore we can say that the spectrum of y is minus infinity less than y less than plus infinity. So in this way, we compute the spectrum of the random variable y. Now, the density function of y, this is the density function of y, f y y. Over here, density function has this kind of transformation formula, fx multiplied by modulus of dx dy. So what is dy dx? dy dx is equal to 1 by sigma. So dx dy should be is equal to simply sigma over here, and this is the expression of the density function fxx. Okay, and you see, ultimately we are going to find the density function of y. So the total expression has to be converted in terms of the real variable y. This is actually a function of x, the random variable, the real variable x. So the total expression has to be converted in terms of the real variable y. And fortunately, we have a very good expression that x minus m by sigma whole square minus half of x minus m by sigma whole square. Over here, this we can directly put x minus m by sigma is equal to y. And this sigma will get cancelled with this sigma, and therefore we would have 1 by root over of twice pi e to the power of minus half y square. That is actually the density function of the standard normal distribution. Therefore, and over here we are specifying the spectrum of y as well. So what we observe that this random variable y follows standard normal distribution. In this second result, the transformation formula would not be strictly monotone increasing, nor would it be strictly monotone decreasing. The transformation formula would not be a monotone formula of monotone function. Okay, if the formula of the function g, this function g is not a monotone function, then what we do? This is an example of such function. Over here, the question says that if x is a normal variate, with mean m and variance sigma square. Remember, I am using this kind of word, variance. What is variance? That will be discussed after few lectures, of course. That means the second part of this chapter we will discuss about this kind of mean and variance. Actually, this m is called, ultimately we will be able to prove that this m is the mean of the distribution and this sigma square is the variance of the distribution. Anyway, we can also consider it in this fashion, that x is a normal variate with parameters m and sigma. If sigma is the parameter of the normal distribution, then sigma square becomes the variance of that distribution. We shall introduce the idea of mean and variance in the subsequent lectures in this chapter. Okay, for the time being, we can consider that x is a normal variate with parameters m and sigma. So m is any real number in between minus infinity to plus infinity, and sigma is a positive quantity. Okay, then what we need to do? We have to show that half of x minus m by sigma square, this kind of expression, half of x minus m by sigma square, this kind of expression follows a gamma distribution. We shall have to show that this is a gamma variate with parameter half. Okay, we know that the gamma L distribution, in case of gamma distribution, L is a positive quantity. So we shall have to show that over here L is equal to half. and this same question comes in a different fashion. Over here, x is a normal variate with parameters m and sigma, and in the previous example, I proved that this expression within this bracket x minus m by sigma, this is a standard normal variate. So this total expression becomes in this fashion half into a standard normal variate, its whole square. Got it? That follows a gamma distribution with parameter half. And this same example is sometimes selected in a different fashion, that if x is a standard normal variate, then prove that half of x square, just similar to this over here, half of the square of the standard normal distribution, standard normal variate, the square of the standard normal variate. So over here, half of x square means half multiplied by the square of standard normal variate. This is a gamma half variate. We can show that this is a gamma half variate. And I would like to mention over here a point which is not related to this example, that it can be shown that only this random variable x square has a different kind of distribution, that is called chi-square distribution, although chi-square distribution has not been introduced formally in over here in our previous lectures, but later on, hopefully not in this chapter, but after this chapter there is one more chapter. There we shall have to prove this type of result, that if x is a standard normal variate, then we can prove that x square follows some kind of chi-square distribution. That we shall discuss later. But over here we are going to show that if x is a standard normal variate, then half of x square would be a gamma half variate. All right. Then how to prove this result? Over here, you see, we have already proved that z is equal to x minus m by sigma is a standard normal variate. So for the time being, we suppose that this is the expression of the random variable y. So we denote it by y. Y is equal to half of x minus m by sigma whole square, and for simplicity, as because we took z is equal to x minus m by sigma, so we can write it as half of z square. So you can say that in place of x, we are considering this random variable z, as because z is a standard normal variate. Now you see over here, the density function z is a standard normal variate, therefore this should be the density function 1 by root over twice by e to the power of minus half z square, and the spectrum of z should be minus infinity to plus infinity. Now over here, if you consider the derivative of y is equal to half of z square, this capital Y is equal to half of capital Z square, therefore small y should be is equal to half of small z square. So if you consider dy dx, the problem is that if we consider dy dx, then dy dx should be is equal to simply z. And z may be positive, z may be negative, so we cannot say that z this is always strictly positive or this is always strictly negative. Both kind of nature, dy dx may be greater than 0, may be less than 0. So both kind of nature holds over here for different values of z. So we cannot directly apply the transformation formula that we proved earlier. So what we do, we actually try to investigate the nature of y, and you see over here, if y is a number in between capital Y, this random variable capital Y varies in between y and y plus dy. Dy is a small quantity, suppose. Then what we observe over here, you see, small y means half of z square, and y plus dy, that would be half of z plus dz whole square, and this capital Y should be is equal to half of capital Z square. Got it? So forget this quantities half, this half, this half, and this half. Forget all this half. So ultimately we will have this type of result, that Z square less than capital Z square, and that is less than Z plus dz whole square. Now try to consider this kind of inequality in this way. Suppose say 4 less than z square, hmm, and suppose that is less than 9. 9 means you can consider it as equal to 3 square, and 4 means you can consider this as equal to 2 square. Hmm. And this result, this kind of result is would be true. If it is true, then we can say that you see 2 less than z, and that is less than, if you consider an equality over here, then equality would come, that is 2 less than z less than or is equal to 3. And similarly we can also consider that minus 3, that would be less than or is equal to z, okay, and that is strictly less than minus 2. So this is one event and this is another event. So whatever be the value of z, whether z lies in this zone or in this zone, for both of these two values of z, z square would also satisfy this type of inequality, that 4 less than z square less than is equal to 9. Or in other words, we can say that this kind of inequality is actually the union of this event and this event. And generally the union is represented by plus. So we can say that this kind of inequality, this kind of event is actually the union of this first event plus this kind of second event. Got it? Now consider this 2 is equal to this z, and this 3, that is 3 square, that is 9. This 3 can be considered to be is equal to z plus dz. Hmm. So what you observe is that you see this expression z square less than z less than is equal to z plus dz whole square. This kind of inequality can be written in this way, that z less than capital Z less than is equal to z plus dz. Hmm. That is actually 2 less than z less than is equal to 3. And over here the second segment of this inequality, that is actually minus 3. This is the representation of minus 3 less than is equal to z less than minus 2. Okay, so in this way we can prove that this inequality, the event represented by this kind of inequality, this is actually the union of this event plus union of this second event. Hmm? And you see these two events, this is actually the positive portion in the z-axis, and this is actually the negative portion in the z-axis. So these two actually two disjoint events, and therefore we can say that this event is actually converted into the union of this event and this event. Hmm. The event y less than capital Y less than is equal to y plus dy. This kind of event is actually the union of this event y less than capital Z less than is equal to z plus dz, and minus of z plus dz less than equal to z less than minus z. Got it? And therefore probability of this kind of event, that should be is equal to the probability of this first event plus probability of this second event, so that we can write the probability in this way, that probability of y less than capital Y less than is equal to y plus dy, that is actually the probability of first event, that is z less than capital Z less than is equal to z plus dz, and minus z plus dz less than equal to z less than z plus less than minus of z. Got it? And now over here we are going to show that probability of this quantity and the probability of this quantity, probability of this event and probability of this event, these two probabilities are same. Got it? And if it is possible to show this result, then in place of writing this term, we can omit this term, and we can simply write a 2 over here. That would be the advantage. So let us first prove this result, that probability of this kind of event and probability of this kind of events are same, and that is very easy to prove. And remember, that would be the key factor of this proof. Hmm. over here you see, uh, over here z less than capital Z less than Z plus dz. This expression can be written as the integral of the corresponding density function of Z dz, of course. And what is the density function of Z? This is the density function of Z, that is actually the density function of standard normal distribution. And in this standard normal distribution, in this integral, just consider the transformation t is equal to minus u. Okay, consider the transformation t is equal to minus u. Then the remaining portion over here, in place of dt we shall have minus du. The lower and upper limit would be changed. In place of z we shall have minus z. In place of z plus dz we shall have minus of z plus dz. And we are just changing the position of z and minus of z plus dz by converting this negative symbol into a positive symbol. Got it? And afterwards we would have this kind of result. You see, this is a definite integral, therefore u can be converted in terms of u can be this integral in terms of u can be again rewritten by an integral in terms of any other real variable z. And what is this? This is actually the density function of the variable z, that is actually fzz. And therefore this would be is equal to the probability that minus of z plus dz less than or is equal to capital Z and less than minus of z, because this lower limit is equal to minus of z plus z dz and upper limit is equal to minus of z. Got it? And that's why this equation number 3, from this equation number 3 we can omit this second term and we can write 2 over here. And this corresponding relation has been written as relation number 4. Sorry, not 4. Has been written in this over here. The probability of y less than capital Y less than y plus dy, that is equal to 2 times of probability z less than capital Z less than is equal to z plus dz. Okay. And what is this? This is actually called the probability differential. I discussed them in our previous lecture, the idea of probability differential. I told you that the probability of very small element like in between y and y plus dy, that is actually that is called the probability differential. And this probability differential can be written in this way: fy of y multiplied by dy, and this expression, this the probability element, this probability of z less than capital Z less than is equal to z plus dz, that can be written as fzz into dz. Okay, so we got this type of result, and fyy, that is actually the density function of y. Okay, fzz is the density function of z over here. And then we can compute this. We can write this dz as equal to dz dy multiplied by this dy. Then what is forget about this dy. You can neglect this to dy. Do not cancel. You can neglect this to dy. The corresponding coefficients must be same. The coefficient of dy must be same on left hand side and on right hand side. Therefore, compare the coefficients of dy. Then on the left we would have fyy, and on the right we would have 2 into fzz multiplied by dz dy. And we considered over here, we started with the fact that z is greater than 0, and if z is less than 0, then also we can prove this result in a similar fashion. All right. So we got a similar result or a similar transformation formula uh, in terms of z. And as because initially we took z greater than 0, then we can say that from this dy dx, from this formula y is equal to half of z square, we can get dz dy. Dz dy is equal to 1 by z. Dy dz is equal to this dy dz, this dy dz, this dy dz, this dy dz would be is equal to simply z. Therefore, dz dy should be is equal to this 1 by z. Got it? So just to put this expression of z, and now what we have, we actually have an expression involving the random involving the real number z, and that real number z, this expression of z has to be converted into the expression of y. And if y is equal to half of z square and we consider z greater than 0, therefore z has to be taken as positive square root of 2 into y. Z has to be taken as positive square root of 2 into y over here. So in place of z, we can put root over of 2 into y, and this root over of 2 into y, just putting z is equal to root over of 2 into y, and after manipulation, what we find? We find that we get the density function of y in this fashion: e to the power of minus y to the power of half minus 1 divided by gamma half. And what was the spectrum? You see over here, whatever be the value of z, half of z square is always greater than or equal to 0. Particularly speaking, this is greater than 0 because we don't ever consider equality in the spectrum. So we can say that y is greater than 0. And similarly, if z is less than 0, in that case also we can prove the same density function of y. So in both of these two cases, we can prove that y has this kind of density function, and the spectrum of y is this spectrum, that means 0 less than y less than infinity. Therefore, we can conclude that the random variable y follows gamma distribution. And what is the parameter of the gamma distribution? This is the parameter of the gamma distribution. From this expression, you can identify the value of the parameter. Over here, L is equal to half. Therefore, you can say that the random variable y follows gamma half distribution. Okay. So in this way, we prove the result that the random variable y is equal to x minus half of x minus m by sigma whole square. This random variable follows a gamma half distribution.